most remarkable feature is agreement with experiment, which I'll elaborate on in a moment. But other ones are where they, in fact, exceed quantum electrodynamics, these non-abelian theories that occur in the description of the strong and weak interactions, have charge quantization or universality of the interaction as an automatic consequence, whereas in the Maxwell equations describing elementary particles, otherwise the relative values of the charges are arbitrary, so that, for instance, the equal and opposite charges of protons and electrons is not understood within the theory, but input to it. And unlike quantum electrodynamics, these enhanced theories actually exist, even non-perturbatively, whereas quantum electrodynamics, famously, if carried to high orders, will break down. So these kind of enhanced theories with beefed up gauge symmetry form the core of the modern standard model. Because of that, without significantly lying or exaggerating, we can write down the core of the standard model on one transparency, and there it is. There are three fundamental interactions being described here: the strong, weak, and electromagnetic interactions. They are based on symmetries of gauge invariance, generalizations, direct generalizations of the Maxwell gauge invariance, but based on the groups SU3, SU2, and U1, the abelian one is the original one. The SU3 acts on vectors that have three components, complex vectors that have three components, so they move horizontally in these multiplets. The SU2 has two component vectors and moves vertically in these multiplets. And the U1 has to be specified as the strength of a coupling that is more arbitrary, as I discussed. There's no reason for it to be quantized at this level. And just phenomenologically, one has these assignments here for the different observed multiplets of elementary particles. And then you have the up and down quarks in three different colors, the neutrino and the electron, left-handed. And then the right-handed components, right-handed pieces of the fields interact differently, reflecting parity violations. Anyway, I won't be able to do justice, of course, to the detailed structure of the standard model, other than to say that if you know the rules of relativity and relativistic field theory and group theory and gauge symmetry, that's all you have to know to reconstruct from what's on this cartoon-like slide the world, the laws of the world as we know it. So we've reduced things to three fundamental forces. Gravity is also another force. We'll come to it later. And six fundamental materials. All the particles within one multiplet should really be regarded as the same particle, because these gauge transformations, these arbitrariness in the description, change one into another. So really, these labels of the different colors, for instance, are arbitrary. And then there's the infamous two repeats with the muon, the tau lepton, and their neutrinos, and the heavier quarks. But that's the core of the standard model, all on one slide, without too much lying. In a form where I said, like, not too much lying, I mean something very specific. You could write a computer program that's relatively compact, that has only the information on that slide, and the computer would be able to calculate for you the mass of the proton and all other physical results of the standard model. so nothing is hidden. Now I'd like to come back to the geometric aspect of gauge symmetry, which is interesting historically and ties together very nicely with the future development I want to discuss. So gauge symmetry was named and realized as a geometrical kind of transformation by Hermann Weyl in 1918. I presented it so far as was developed in the history of electromagnetism as kind of an arbitrariness in the description of a mathematical trick. Hermann Weyl in 1918, in an attempt to give physical meaning to it and to exploit the new insight into space and time offered by general relativity, had a geometrical interpretation of that transformation, of that arbitrariness in the description of nature. This, by the way, is why gauge transformations are called gauge transformations. They weren't originally called that. The gauge is the length of something, the measure of something. It comes out of Weyl's paper. So, general relativity, properly understood, postulates symmetry under local Lorentz transformations. You can make Lorentz transformations independently at all different points of space and time. This was actually also first properly understood in Weyl's paper. I think Einstein didn't really understand it properly. In any case, Weyl proposed a larger symmetry, including not only the ability to make independent Lorentz transformations at different points in space and time, but also local scale transformations, so just blowing up the size of everything independently at different places in space and time. That's one parameter for every space-time point, so it has the same count of degrees of freedom, if you like, one field, just like in a gauge transformation. And if you set up the mathematics of demanding invariance of your equations under that kind of transformation, in parallel to the way you get general relativity by demanding invariance of your equations under local Lorentz transformations, you get something that very much resembles Maxwell's equations. However, you get too much. You get the Maxwell's equations, but also restrictions on the kinds of couplings that can occur that run you into trouble phenomenologically. Basically, you derive that all particles are strictly massless, contrary to observation. Ironically, this sort of trouble is precisely the kind of trouble we now know how to cure with spontaneous symmetry breaking. I'll come back to the issue of whether we can revive Weyl's idea momentarily. But in any case, when quantum theory emerged, which was after 1918, in the modern form in the mid-1920s, Weyl and also Fritz London immediately recognized how to adapt the mathematics that Weyl had developed for scale transformations to the new possibilities offered by quantum mechanics. In quantum mechanics, the appropriate scaling, which in Weyl's theory was a scaling of space and time, is instead taking place in an auxiliary space, a phase space, kind of in the sense of complex numbers used to describe the electron wave function or wave function of other particles. And instead of a blowing up of that phase, of that state, you make rotations. So instead of multiplying by real numbers, you multiply by imaginary numbers of order of magnitude unity, and the same mathematics, however, applies. What about Weyl's original idea? Could there be spontaneously broken, so hidden, local scale invariance with an associated new field? Probably not. The difficulty is that local scale invariance, even when valid classically in your equations, can't be maintained in quantum theory. This is an example of what we call an anomaly. So we say the symmetry, you have a symmetry of the classical theory that can't be maintained in the quantum theory. We say it has an anomaly or anomalous. The reason is the phenomenon of vacuum polarization, and spontaneous fluctuations in the vacuum. This is an actual numerical simulation of spontaneous fluctuations of the gluon fields in QCD. And the point is that the smaller fluctuations in an interacting theory affect the magnitude of the bigger fluctuations, and so they're not scale invariant. The bigger ones are different from the smaller ones. Even if the underlying classical equations were invariant. These non-scaling effects have been observed in many circumstances and studied in quantitative detail in QCD. They've also been discerned in QED and weak interactions where they're much smaller, but can be seen in actual experiments. So here is the data in QCD. Many experiments show that the strength of radiation, which is described by a dimensionless quantity, the analog of the fine structure constant for QCD, changes with distance, or equivalently in quantum mechanics, or dually, I should say, with energy, and the prediction for how that should change is beautifully verified now by a rich variety of experiments leading to a consistency across many energy scales. And this has now received the official seal of approval. So, to tie up this circle of ideas, I'd like to discuss a development that enhances the symmetry of the world, perhaps, and brings in scale invariance in a different way to complete the story. So the standard model, as I showed you on one slide, its core is very compact, extraordinarily economical, given how much it describes, but still not perfect, because 3 forces are more than 1, and 6 different kinds of materials is more than 1, and we like, and since the theory is based on symmetry now, they're all based on gauge symmetry, similar kinds of mathematical structure, it's begging you to make a bigger symmetry that includes them all. And, of course, the rules for combining symmetries are well developed, the theories of Lie groups, and so one of the simplest things you can try is that includes SU3 cross SU2 cross U1 is SO10, and when you do that, the matter particles fall into place very cooperatively so that you get an irreducible representation with spinners that accounts for all those lopsided structures within the standard model. Beautifully. They have been lopsided in any other way, or if those funny numbers for the charges have been different, it wouldn't have worked. So we have one material, one force. At first sight, this unification appears to go too far, since the observed strong, weak, and electromagnetic couplings are not equal, as full symmetry would require, that universality I alluded to. But here, the quantum violation of scale invariance may come to our rescue. The different gauge couplings, though classically scale invariant, change with distance, as we've already seen, due to vacuum polarization. We can calculate that effect. If we calculate it using the known particles, we get a tantalizing but quantitatively faulty result. If we extrapolate the observed couplings down to shorter distances, stripping away the effects of vacuum polarization to see if there's an underlying unification, with the experimental and theoretical uncertainties indicated by the width of these lines, they don't quite meet, although they seem to want to.